I've said before that an ECH 3023 will only be solving separable differential equations. However, in your future classes and in the rest of your life as a chemical engineer, you'll be expected to solve non-separable differential equations too. So for this class, I want you to be able to know how to deal with a non-separable differential equation, and that may involve solving it analytically, even though we won't focus on solving it analytically in this class. I wanted to teach you how you would solve these numerically. So to do that, we'll use Euler's method. Once again, we'll just jump straight into an example problem. And in this video, I'll work out the theory of how to solve it. And then the next video, I'll show you how to actually do this in Microsoft Excel. So I've omitted the problem statement here and I've gone straight to the diagram. And what's going on here is it's a coupled set of mixing tanks. So in the first mixing tank, at my initial time is equal to 0, I've got a saltwater solution that has an initial concentration inside of 2 grams per liter of salt. And this is a flushing problem. So I'm going to flush the salt out of this tank. So in order to do that, I'm going to send 25 liters per second of pure water. And I know that the water is pure because my concentration of salt in this stream is 0. And that is going to be sent to the mixing tank. I'm going to assume that it's well mixed such that the outlet of salt has the same concentration in this stream as it has in the first mixing tank. And then I'm going to send that to a second mixing tank, which is initially pure, so 0 salt concentration in the second tank. And this has an outlet concentration because this one is well mixed as well. And my question is, what is the concentration of salt in this second tank? So this problem may look familiar. I think I gave you the first part of this problem before, but we'll just quickly recap. So in order to solve for CS2, which is what the problem is going to want me to do, or to sketch what CS for the mixing tank of 2 looks like as a function of time, I first have to know what CS1 looks like as a function of time. Just qualitatively, I already know that what the shape of CS2 as a function of time must be. So I know that it's going to start at 0 because that, again, is my initial condition. But I know that it is going to start to increase, and it increases because after time for immediate time, so like right after time 0, I'm going to be inputting some salt water. All right, so I'm going to be inputting salt water into this tank with an initial concentration of 2 grams per liter, right? So at CS of time 0, this is equal to 2. Let me write it like this. CS1 of 0 is equal to 2. So I'm going to be increasing my salt concentration. But after a while, CS1 is going to be decreasing as a function of time. My concentration of salt is going to decrease after that. So there's going to be some maximum value. And I'm interested in, again, what this whole profile looks like. So let's do the first mixing tank. First of all, I got V0, V1, and V2 are all equal to the same thing. So my volumes are all going to be consistent. And actually, I need to know what the volume of these tanks are as well. So let me pencil that in. These are both 500-liter vessels. Or that we'll say that the volume inside is 500 liters, and those are constant. All right, so my CS1 of t, I first have to solve for that. So we'll start by doing a mass balance. The mass of salt in the tank with respect to time, the change of mass of salt in the tank with respect to time is MS1, or MS in, we'll call it, minus MS out. And that, let's see. I want to express the mass in terms of a volume times a concentration. So volume times a concentration. D CS1 times V dt is equal to V0. I'm just going to call it V dot again because they're all equal. Right? So V dot is going to be V0, V1, and V2 times CS naught, and that is 0 because it's pure water. The mass of salt out is V dot times CS1. And let's see, V is going to be factored out of the derivative. So dCS1 over CS1 is equal to minus v dot over v dt. And just real quick, because we've seen this exact problem before, ln of CS1 is equal to minus v dot over v times t plus a constant c. Take the exponent of both sides, get CS1 is equal to c times exponent of minus v dot over v times t. Plugging in my initial condition, which is that CS1 of time 0 is equal to 2. 2 is equal to c times 1, and therefore c is equal to 2. So coupling these together, CS1 of t is equal to 2 times exponent of v dot, which is 25 over 500 times t. All right. Again, we've solved this problem before. This solution procedure should look somewhat familiar. However, solving for CS2 is going to be a similar procedure, but it's going to be complicated a little bit. So let's do that. Let's do a balance on tank 2, balance on salt for tank 2. All right, same form, right? Accumulation is equal to input minus output. So dms2 over dt is equal to ms in minus ms out. And the expressions for in and out, the in is not 0 anymore. So that's why this is a little bit more complicated. So V is still the same. This is the volume of tank 2. Volume of salt water in tank 2, to be more precise. V times dCS2 by dt is equal to V dot CS1 minus V dot CS2. And if I just do one more line of algebra here to get my final differential equation, dCS2 by dt is equal to V dot over V, CS1 minus CS2. And now I've got a bit of a conundrum. I don't have a separable differential equation here. And the reason why it's not separable is because I can no longer separate variables, right? So if I wanted to solve this differential equation, it would be improper to do the following, to say dCS2 over CS1 minus CS2 is equal to V over V dot dt. I can't do this. And the reason why I can't do this is because CS1 is a function of t, right? I know this is changing with respect to time. Therefore, if I'm separating variables, I have to have all the stuff that's a function of t on the one side and all the stuff that's a function of CS2 on the other side. And I know this is a function of t because if I plug in what I know that it is, this is 2 times exponent of minus 25 over 500 times t, right? So therefore, I can't solve this. This is an improper step, by the way. And to just go one more step here, it's going to be V dot over V. And CS1, I'm going to plug in what I know CS1 to be. So let's see, what 2 was my, trying to avoid plugging in numbers here, but I've already plugged in numbers, so I guess I'll keep it. V dot over V times 2 exponent of minus 25 over 500 t minus CS2. And once again, this is not separable. However, you may, from your differential equations class, know how to solve this. So this is solvable by a procedure called the integrating factor. Solvable with an integrating factor. And if you're comfortable with integrating factor, if you're comfortable with solving these, I encourage you to try this. But as I've said before, I'm not going to expect you to know how to solve this analytically. If you're curious, I have what the answer is, by the way. So I'm skipping a lot of steps. So CS2 of t, actually. I sometimes I mix up my notation. CS2 of t is equal to t over 10 divided by exponent of t over 20. So once again, that's the answer for you. If you'd like to try this on your own, putting that knowledge from differential equations to good use, Or if you don't remember how to do an integrating factor, once again, in the next video, I'll show you how to do it with what's called the Euler method. So that's going to wrap up this video. Oh, before I do that, I actually want to make a quick note about, even though I don't expect you to be able to solve this analytically, there's still some things I could expect you to be able to do. For example, I could expect you to be able to draw this, to do a sketch of this plot without putting numbers into it, right? So I expect you to know that it's going to start at 0, it's going to initially increase and then decrease again. I know that my long-term behavior as t tends to infinity is going to tend towards 0 again. And I know that because I'm flushing pure water. And if I wait long enough, I'm just going to have pure water everywhere in the system. All the salt is going to be flushed out. So I still do expect you to be able to do that. You could also, or maybe not for this problem, by setting the derivative equal to 0, you could solve for the t at which CS2 is equal to 0. Actually, I don't think you can. Yeah, because okay, never mind that I said that. I'm going to wrap up the video here. Once again, in the next video, I'm going to show you how to solve this with Euler's method. See you there.